Preparing for a software engineering at Akamai interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a globally distributed content delivery network? I would place cache servers near users and route requests to healthy, low-latency edges using DNS or Anycast. Misses would fetch content from an origin, ideally through an origin shield to reduce duplicate requests. I would define TTLs, purge APIs, stale while revalidate behavior, and protection against cache stampedes. Global health checks would remove failing regions automatically. Metrics should include hit ratio, P95 latency, origin load, and error rate. The design prioritizes fast reads while accepting controlled freshness trade-offs. While answering, cover edge locations, DNS or Anycast routing, origin shielding, caching policies, cache invalidation, health checks, load balancing, observability, security, and latency versus consistency trade-offs. Question 2. Explain how a CDN cache works and how you would improve its hit ratio. A CDN cache stores responses using a cache key, usually built from the URL, method, host, and selected headers. I would improve hit ratio by normalizing URLs, choosing appropriate TTLs, compressing variants, and caching popular objects at regional or edge layers. I would avoid including irrelevant query parameters in keys. For dynamic or personalized responses, I would bypass caching safely. Monitoring hit ratio alongside freshness and origin errors prevents optimization from creating incorrect responses. Make sure to cover cache keys, TTLs, HTTP headers, cacheable methods, normalization, object popularity, regional caching, purging, negative caching, and the risk of serving stale or personalized content. Question 3. How would you implement cache invalidation for millions of edge servers? I would make purge requests idempotent and assign each one a unique version. A control plane would publish invalidation events through durable regional queues, then edge agents would acknowledge processing. Retries would use exponential backoff, while dead letter queues handle persistent failures. For frequently changing assets, versioned URLs reduce purge pressure. The system should expose propagation status, age, and regional completion metrics. I would favor eventual, bounded invalidation rather than attempting synchronous global coordination. In your answer, discuss purge APIs, versioned objects, propagation fanout, retries, idempotency, ordering, acknowledgements, failure handling, and how to measure completion without overwhelming the control plane. Question 4. What happens during a cache stampede, and how would you prevent it? A cache stampede occurs when many requests discover an expired object simultaneously and overload the origin. I would allow one request to refresh the object while others wait briefly or receive stale content. Stale while revalidate and probabilistic early refresh reduce synchronized expiry. Locks should be scoped per object and have timeouts, preventing deadlocks or a global bottleneck. I would also enforce origin rate limits and monitor refresh concurrency, miss bursts, and upstream latency. Be sure to mention synchronized expiration, request coalescing, locks, stale while revalidate, probabilistic early refresh, origin protection, timeout budgets, and the dangers of a single global lock. Question 5. How would you route a user to the best Akamai edge server? I would combine Anycast or DNS routing with continuously updated telemetry. Candidate edges should be evaluated using network latency, packet loss, available capacity, health, and ISP-specific performance rather than geography alone. DNS answers can use short TTLs for steering, while Anycast offers simpler client behavior but less precise control. When an edge or region degrades, routing should shift gradually to avoid overload. I would validate decisions using real user latency and error metrics. Focus on DNS-based and Anycast routing, latency measurements, network proximity, capacity, health, geography, ISP behavior, failover, and why the nearest physical location is not always optimal. Question 6. Design a rate limiter for a globally distributed API. For each customer, I would use a token bucket with a refill rate and burst capacity. An edge can enforce local limits cheaply, while a centralized or regionally replicated counter handles stricter global quotas. I would define whether limits apply per API key, user, IP, or endpoint. Approximate limits are often preferable to cross-region coordination on every request. During data store failures, I would choose fail open or fail closed based on abuse risk, then expose clear retry metadata. Cover token bucket or leaky bucket algorithms, distributed counters, identity dimensions, local versus global enforcement, clock issues, burst handling, consistency, fail open behavior, and administrative overrides. Question 7. How would you detect and mitigate a DDoS attack at the edge? I would establish baselines for traffic volume, connection rates, protocol distribution, request paths, and response codes. Sudden deviations could trigger edge filtering, rate limits, challenge mechanisms, or upstream scrubbing, depending on attack type. Anycast helps absorb volumetric traffic across many locations, while WAF controls target application layer abuse. Mitigations must be staged and reversible because legitimate flash crowds resemble attacks. I would track blocked traffic, false positives, origin load, and customer visible latency. Discuss volumetric, protocol, and application layer attacks, baseline modeling, rate limits, traffic filtering, scrubbing, anycast absorption, WAF rules, customer impact, and safe rollback of mitigations. Question 8. What is consistent hashing, and where would you use it in Akamai-like infrastructure? Consistent hashing maps both keys and servers onto a logical ring. A key is assigned to the next server clockwise, so adding or removing a node remaps only a fraction of keys instead of reshuffling everything. Virtual nodes improve balance when machines differ in capacity. I would use it for cache ownership or partitioning requests across edge workers. Replicas improve availability, while hotspot detection remains necessary because a popular key can still overload its assigned node. In your answer, explain hash rings, virtual nodes, minimized remapping, node membership changes, replication, hotspots, and applications such as cache assignment or distributed request routing. Question 9. How would you design a fault-tolerant service across regions? I would deploy stateless service instances across independent regions and route traffic using health-aware global steering. Data replication would depend on business requirements. Asynchronous replication improves availability, while synchronous replication increases latency and limits geographic separation. Each dependency needs timeouts, retries with jitter, circuit breakers, and fallback behavior. I would define RTO and RPO explicitly, automate failover, and regularly test regional loss. A healthy design continues serving reduced functionality rather than failing entirely. Mention redundancy, failure domains, health checks, replication models, traffic failover, data consistency, recovery objectives, graceful degradation, dependency isolation, and testing through fault injection. Question 10. Explain the difference between TCP and UDP, and when you would choose each. TCP provides an ordered, reliable byte stream with retransmission, flow control, and congestion control, making it suitable for HTTP and content delivery. UDP is connectionless and has lower overhead, but applications must handle loss, ordering, or congestion themselves. I would choose UDP for latency-sensitive traffic such as telemetry or real-time media when occasional loss is acceptable. Reliability is not automatically better with TCP. Its retransmissions can create head-of-line blocking. The application's delivery requirements should drive the choice. Be sure to cover connection establishment, reliability, ordering, flow control, congestion control, overhead, latency, packet loss, and examples involving HTTP, DNS, streaming, and real-time traffic. Question 11. How would you troubleshoot high latency in a CDN request path? I would decompose latency into DNS, TCP or Quick Connection Setup, TLS, edge processing, cache lookup, and origin fetch time. Comparing cache hits with misses immediately narrows the search. I would segment P50, P95, and P99 by geography, ISP, protocol, object, and edge location. Distributed traces and packet-level telemetry can reveal retransmissions or slow dependencies. After identifying the bottleneck, I would change one variable, run a controlled comparison, and verify customer impact. Cover client, DNS, connection setup, TLS, edge processing, cache misses, origin latency, packet loss, geographic patterns, P50 versus tail latency, tracing, and controlled experiments. Question 12. What strategies would you use to reduce tail latency in a distributed service? Tail latency usually comes from overloaded queues, slow dependencies, or uneven work distribution. I would set strict timeouts, reuse connections, limit queues, and shed low-priority work before saturation. Hedged requests or redundant replicas can reduce extreme delays, but only with cancellation and traffic budgets because they amplify load. I would monitor P95 and P99 rather than averages, inspect correlated dependency latency, and use admission control. Predictable degradation is preferable to unbounded waiting. Discuss queue control, bounded retries, hedged requests, replication, connection reuse, batching, load shedding, admission control, percentile monitoring, and the risk of multiplying downstream traffic. Question 13. How would you build a service that handles millions of concurrent connections? I would use event-driven, non-blocking I/O so a small number of threads can manage many sockets without one thread per connection. Connections need explicit memory budgets, idle timeouts, keep-alive limits, and backpressure for slow readers or writers. Load balancers should distribute connections consistently while health checks detect overloaded workers. Kernel and file descriptor limits must be tuned, but application safeguards matter more. I would test connection churn, slow clients, packet loss, and abrupt mass disconnects. Focus on event-driven I/O, EPOL or KQ, connection limits, memory accounting, keep-alives, backpressure, kernel tuning, load distribution, timeouts, and protecting the service from slow clients. Question 14. Describe a robust approach to concurrent programming and avoiding race conditions. I first identify shared mutable state and reduce it through immutable data or ownership boundaries. For unavoidable sharing, I choose the smallest synchronization mechanism, atomics for simple counters and locks for compound invariants. Locks need a documented order, limited scope, and clear ownership to prevent deadlocks. I also avoid holding locks during network calls. Stress tests with randomized scheduling, race detectors, and invariant checks are essential because ordinary functional tests rarely expose timing-dependent failures. In your answer, include shared state identification, immutability, atomic operations, locks, lock ordering, condition variables, ownership, deadlock prevention, and stress or race detector testing. Question 15. How would you design a reliable distributed job queue? I would persist jobs before acknowledging producers and give workers a visibility timeout while processing. A worker acknowledges only after the side effect succeeds, otherwise the message becomes available again. Because retries can duplicate work, handlers must be idempotent using request keys or transactional state. Exponential backoff and dead letter queues isolate poison messages. If strict ordering is required, I would partition by key and accept reduced parallelism. Metrics should expose queue age, depth, retry rate, and worker throughput. Mention durable messages, visibility timeouts, acknowledgements, retries, idempotent workers, dead letter queues, ordering requirements, backpressure, poison messages, and delivery guarantees. Question 16. Which data structures would you choose for an LRU cache, and why? An LRU cache typically combines a hash map with a doubly linked list. The map provides O(1) lookup, while the list keeps most recently used entries at the front and evicts the tail in O(1). Reads and writes move nodes, so concurrent implementations need a lock, sharding, or carefully designed synchronization. I would also consider entry size, TTL expiration, and negative caching. For distributed caches, local LRU becomes only one layer of the policy. Be sure to explain the hash map plus doubly linked list design, 1, lookup and eviction, capacity handling, concurrency, memory overhead, and alternatives for weighted or distributed caching. Question 17. How would you optimize a solution that finds the top k most frequent URLs? For a bounded dataset, I would count URLs in a hash map, then maintain a minute heap of size k, giving O and log k selection after counting. If frequencies are tightly bounded, bucket sorting can be faster. For streaming CDN logs, I would aggregate counts by partition and merge local top k candidates, while approximate heavy hitter algorithms reduce memory. I would clarify whether exact results are required, because sketches trade small error for substantially lower storage and network cost. Cover frequency counting, hash maps, min heaps, bucket sorting, streaming constraints, heavy hitters, memory limits, distributed aggregation, and the difference between exact and approximate answers. Question 18. Tell me about a production incident you handled and what you learned. In one incident, a configuration rollout caused elevated cache misses and origin overload. I first confirmed the error and latency increase through dashboards, then paused deployment and redirected traffic while comparing healthy and affected edges. We restored the previous configuration, communicated status at regular intervals, and verified recovery through origin load and hit ratio metrics. Later, we added staged rollout, automated validation, and rollback thresholds. The key lesson was treating configuration as production code with tests and observability. Make sure to structure the response with situation, impact, diagnosis, actions, communication, recovery, root cause, prevention, and measurable improvements without assigning blame. Question 19. How do you balance performance, reliability, and security when designing an edge feature? I start by defining the feature's latency budget, availability target, data sensitivity, and abuse cases. Security controls such as authentication, authorization, validation, encryption, and resource limits must be designed into the request path, not added later. I would keep hot path work bounded, cache safe decisions, and degrade gracefully when auxiliary services fail. Progressive rollout with guardrails lets us compare performance, errors, and attack signals. The best design makes secure behavior the easiest default. Discuss threat modeling, secure defaults, authentication, authorization, input validation, resource limits, latency budgets, graceful degradation, privacy, rollout controls, and measuring competing objectives. Question 20. Why do you want to work at Akamai, and how would you contribute as a software engineer? Akamai interests me because its software operates at the edge of the internet, where milliseconds, resilience, and security directly affect millions of users. My experience building distributed services, diagnosing production issues, and improving performance fits that environment. I enjoy understanding failures across application, network, and infrastructure layers, then turning lessons into automation and safer designs. I would contribute pragmatic coding, strong operational ownership, and collaborative problem solving while continuing to deepen my networking and edge computing expertise. In your answer, connect Akamai's edge platform, internet scale reliability, security, networking, customer impact, and your specific experience with distributed systems, debugging, ownership, and collaborative engineering. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.